Hello again. In this last part on using inductive families to do derivability, we are going to look at how we can actually prove something about the proof system itself. So let's prove that we had this system up here, which was using variables or hypothesis and abstraction. Let's prove that we can actually replace these concepts with another system where we keep the application, but instead we have just the combinators K and S, which you might remember from combinatory logic. So we keep the application and we have these two combinators instead of abstraction and variables. And because we have no variables, we see that there are actually no contexts needed here, right? It's just a system where we say which formulas are derivable. And we're not using abstraction, we're using S and K, an application instead. And our claim is that we can translate between these two systems. So if something is derivable in this system, then it's derivable in the other one for the empty context and vice versa. Right? So let's see if we can prove this. Let's do the easy direction first, where we start with something in this system and give a derivation in the other one. And the way we do this is by pattern matching on the derivation, right? So we see that this derivation is either an application or a K or an S, right? And if it is an application, then we also have an application in this system, so we can just translate it to an application, and then we can translate both of the subderivations recursively like this, right? So that was easy. For S and K, we actually have to do some work. Let's do K first because it's easier. So here, since K here says that there is a derivation of this formula, we have to give a derivation of that formula in the other system. And we see that it's a derivation of an implication. So the standard way to do this is by using abstraction. And here again, we have a derivation of an implication. So we do another abstraction. And now here, we have to derive an A. Well, we have an A in our context, but we first have to weaken past this B. Okay, and now here we have to give a derivation of A given that we have an A. That's exactly the hypothesis. Right. Okay, so we could do that. And now we just have to do the same thing for this more complicated formula. Well, it's also going to start with some abstractions, right? Well, it's still deriving an implication, so that's an abstraction. Still deriving an implication, that's an abstraction. Okay, and now we have to derive a C. Well, this thing is going to give us a C if we apply it to something. Okay, and here we still need something to give us a C. Well, that's going to be the application of that thing to a final thing. Alright, so this thing is going to be the 1/3 assumption, so we're going to weaken twice. And now here, this is the hypothesis we want. Okay, and now here we need an A, but we have an A as our most recent hypothesis. And here we need a B. Well, we can get the B if we apply this thing to that thing. It's going to be an application of something to something. Well, this is the second thing, so that's weakening of the hypothesis. And this is just going to be the most recent thing, so that's that. Okay, so that's of course is completely impossible to read now. And it's only slightly easier to write if you do it yourself. So if you want to understand it, I would recommend that you get this file and then you delete this line and you start to try to fill it in yourself. But it's just writing a lambda term in a complicated language like this. So that's good. We've managed to translate from the system to this one, right? Let's see if we can go the other way. We start the same way, we pattern match on the D. Looks quite promising. There's only 2 cases we have to consider. Okay, and this one is easy, right? Because we have an application in both systems, so we just do a recursive call. Okay, what about this one? Well, we have a D, but now we see that there's actually going to be a problem, because we most likely would like to do a recursive call on the rest of the derivation, right? But if we try to do that, then we get a type error, because this function here that we're trying to define, it only works on the empty context, right? But this D is after an abstraction, which means that D is in a non-empty context. So that just doesn't work. And it is never going to work. So what we have to do instead is we have to try and generalize this. So say generalize, which is a standard trick. Right? So if it doesn't work because we're too specific, then let's try to work for an arbitrary context, and then in the end we can always instantiate gamma to be the empty context to get the thing we really want. Okay, but if we try to do this, then we see here that we have a problem, because now we have to derive something that derives A in this system, but we are given absolutely nothing. And if you think about what the problem is that this thing here on the left has some relationship with the gamma, but this thing here on the right isn't talking about gamma at all. So of course A could be derivable or not depending on what's in gamma, but that's not reflected here on the right. So this is also not going to work. Yeah. The reason is because this does not talk about gamma. So what we have to do is we have to come up with some way of making also this system take the context into account. So we didn't think we needed a context, but we'll see that it's actually useful as an intermediate step to have a context.